Okay, in this video I'm going to talk about the arithmetic derivative. So this is a function from natural numbers to natural numbers that is supposed to be kind of similar to the regular derivative of functions. First, we want to make it similar not to the additive properties of the derivative, but to the multiplicative properties. So we have the rule, the product rule, that if we have this is the ordinary derivative. So if we have function f and g, then the product of the function f and g, the derivative of the product, is calculated as the derivative of f multiplied by g plus f multiplied by the derivative of g. So this is basically the product rule, and we want to make something similar for the function from natural numbers to natural numbers. So that's basically the idea. So basically the derivative d is defined. So okay, so I will remove this. So the arithmetic derivative is defined by two equalities. So first for any prime number, for any p such that p is prime, the derivative of this of a prime number is always 1. So that's the first rule, and then the second rule is that the derivative of the product of any two numbers is equal to m multiplied, or let's write this way, is equal to d of m multiplied by n plus m multiplied by d of n. So this is exactly the analog or the equivalent of the product rule for a regular derivative. So so basically we make it a base for the prime numbers, and then this defines basically the derivative of the product. And notice that these two rules fully define the derivatives, fully define the arithmetic derivative. So d of any number can be calculated from these two rules, because a number is always can be represented as a product of smaller numbers, right? So so either it is prime, in which case the arithmetic derivative is defined, or it is not prime, and then it can be represented as a product of two smaller numbers, and in which case we reduce d of this product to the definition of d for smaller numbers, right? So we, using this rule, the second rule, we reduce the definition of d of mn to the definition of two smaller numbers, and then we apply again the same rule to this smaller m and n. Either they are prime, or they can be represented again as a product of two smaller numbers, and so on. So let's find the derivative of some specific number. So let's say d of 60. So, and by the way, so yeah, so although these two rules define fully the arithmetic derivative, we haven't yet proved that the definition is correct. So it might be, technically it might be that when the number is represented in two different ways. So let's say if we have some number that let's say some number a that can be represented as m multiplied by n, and also as m prime multiplied by n prime. Or maybe prime is not a good, because prime can be confused with the derivative itself. And this is, by the way, another notation. So we use the notation capital D to indicate that this is a function, but sometimes like d of n sometimes is also denoted as n prime. So this is another notation for arithmetic derivative. So we will avoid using prime for a natural number. So let's say that it's n1 multiplied by m1 multiplied by n1, and is also represented as m2 multiplied by n2. Then using this, the second rule, we would have basically two. So d of a then would be represented as d of m1 multiplied by n1 plus d plus plus m1 d of n1, and is also would be represented as d of m2 multiplied by n2 plus m2 multiplied by d by n2. And so it's not clear why, like if we then reduce, we would reduce each of them using the same rules to the prime numbers. It's not clear why we would eventually get the same number, the same result, if we use these two representations. So the correctness of the definition is not like we need to prove that this definition is correct. But so for now, let's calculate d of 60, like to give a specific example. So d of 60, so the derivative of the number 60. So 60 is represented as 60 is 4 multiplied by 5 multiplied by 3, right? So first, okay, so let's choose some representation. So 4 multiplied by 15, let's say. So 4 multiplied by 15, this can be represented as d of 4 multiplied by 15 plus 4 multiplied by d of 15, right? Now d of 4, so 4 is 2 by 2, so this would be equal to d of 2 multiplied by 2 plus 2 multiplied by d of 2, right? So this we represented d of 4, this is multiplied by 15 plus 4 multiplied by d of 15, and d of 15 is 15 is 5 by 3, 5 multiplied by 3, so this is d of 5 multiplied by 3 plus 5 multiplied by d of 3, right? So now d of 2, this is equal to 1, because 2 is a prime number. This is equal to 1. D of 5 is equal to 1, and d of 3 is equal to 1, right? So let's rewrite now this expression. So we have 1 by 2 plus 2 by 1 multiplied by 15 plus 4 multiplied by 1 by 3 plus 5 by 1, right? And so this is equal to what? So 2 and 2 would be 4 multiplied by 15 plus 4 multiplied by 3 plus 5, this is 8. Right? So 4 by 15, this is the original number 60. Plus 4 multiplied by 8, so this is 32, right? 32, and in total we have basically 92. So this is the answer. So d of 60, so the arithmetic derivative of 60 is 92. So this is like really a function from natural numbers to natural numbers. Okay, so now let's return to the question of correctness, right? So if we have chosen here some different representation of 60, so let's say 2 by 30, started from 2 by 30 and expanded this using the two rules, then where is the guarantee that we would eventually get the same number 92? Like this is what we need to prove. So, and it can be proven in the following way. So first, like as already mentioned, so these two rules define the function uniquely. So like the function is fully defined by these two rules. So there is no ambiguity, because like we can always expand the number to a smaller number. Either it is prime, or we can reduce it to the function d of two smaller numbers. So we are going to just give the explicit expression for this number, for this arithmetic derivative. And this is this is useful not only for the to prove correctness, but this is useful just in general. So the expression is so first let's notice that so let's say that the number n is represented as a product of prime numbers, right? So so first let's write it as p1 and so on, pk, or we will write it as a product of pi, and the product is by the index I varies here. So the prime numbers here can repeat. So these prime numbers can contain duplicates. So so let's write this can contain duplicate prime numbers, duplicates. And this is just not to introduce the complexity with the power. So alternatively, we could write that this is a p1 in some power k1, and so on, pl in the power kl, and so this would be a product of by index I of the pi to the power ki. But so that not to deal with these powers, it would be easier just to write the product of prime numbers, but remembering that there could be repetitions of prime numbers there. And so then the derivative, so I claim that the derivative of the number n can be defined as so from this number n, can be defined as, let's write t of the product of pi can be defined as n multiplied by the sum of 1 over pi. So this is the explicit formula for the arithmetic derivative. And so like just so to see where we get this, basically when we there is a kind of an extended formula for the product rule. So when there are multiple, so the derivative of let's say n1 and so on nk, so the extended product rule would be like similar to the ordinary derivative. So this would be like n1 multiplied by the derivative of everything else, and everything else is basically n1 multiplied by nk over n1, right? Because we excluded n1 from this product. And then the second would be n2 multiplied by the derivative of this product over n2. We excluded the n2 from this product, and so on. And the last one would be nk multiplied by the derivative of n1 multiplied by nk over nk. So like we have not proved this yet, so this is kind of just analogous to the ordinary derivative, but like it could be proved. I'm just trying to explain where this expression for the formula come from, and so then when we express the d of n as d of the product of pi, this is basically would be this would be the sum. So similar here we have the sum, and then would be pi, so the sum by pi multiplied by the derivative of the original number, right? The original number. So the original number is n over pi, right? So this is like I directly rewritten this formula here, and no, excuse me, no, this is not correct. Yeah, so it should be not the derivative here, but so the derivative should be of n1. The derivative of n1 multiplied by this. So yeah, so like I mixed the place of the derivative. So the derivative of n2 multiplied by this number and so on, plus the derivative of nk multiplied by this number. So here we have the derivative of pi multiplied by this. So n can be n is a common multiplier, right? So we can write that it's n multiplied by the sum of t of pi over 1 over pi, the sum by I. And so d of pi, this is simply 1 because pi is a prime number, right? So this is the product of prime number. And so this would be n multiplied by the sum of 1 over pi. So this is basically exactly the formula that I've written. So yeah, so like it's not written out of nowhere, like it makes sense to write it this way. But now but what I've given here, it's not a proof that the derivative would be this, because I used this extended or generalized rule for the generalized product rule for the product of multiple numbers, which we didn't prove. So the only thing that we know for the derivative is only the product rule for two numbers, the product of two numbers. So it's not a proof, it's just kind of a motivation, like where this formula come from. But once we've written this problem, like the only thing that we need to establish is that, so basically now we start with this definition, and we simply ascertain that that it satisfies both of our rules from which we started, right? So when we define, like let's like we can even use some different, not d of n, but let's say d1 of n or something like that, and then we, so if d, okay, so let's write here. So the so let's define d0 of n as n by the product of 1 over pi, and where pi is the prime divisors of n. And so now we need to prove that d0 of n is equal to d of n. So for that we just need to establish that this d0 satisfies both of these rules. So when we have, yeah, and here like we need, let's write the d0 of n yeah, so d0. So d0 of a prime number when p is prime, so p is prime. So d0 of p, so this would be p by definition multiplied by the sum of 1 over p, but the sum so the sum would be consist of only one term, so 1 over p. This is the only term in the sum, because p is the only prime divisor of p. So, and this of course is equal to 1. So the first property is satisfied, and the second property, so this is first, and the second property is d0 of m multiplied by n is equal to d0 of the product of pi. So let's say that m is the product of pi and n is the product of qj. So pi is the prime divisors of m, and qj is the prime divisors of n. And again, they could be repeated. So pi are not necessarily different. There could be duplicate prime numbers. So by I multiplied by the product of qj by j, and so this whole so mn would be represented as the product of these prime numbers pi and qj, and by definition this would be defined as mn multiplied by the sum of 1 over pi plus the sum of 1 over qj, right? So this is the definition, and now we can expand this, simplify this as, so when we multiply, so notice that m, so let's write this, so m multiplied by the sum of 1 over pi, like this, multiplied by n plus m multiplied by n multiplied by the sum of 1 over qj by j. So like this, I simply like grouped differently this expression. So, and this would be equal to, so this expression is exactly d of m, and this expression is exactly d0 of n, d0 of m, and this is d0 of m. So so the total is so the total is that we have d0 of m multiplied by n plus m multiplied by d0 of n, and this is exactly, so this is exactly the rule 2, the product rule of the derivative. So our function d0 defined in this way, it does satisfy both of these rules, both rule 1 and rule 2. We just checked. So because of this, and because these two rules are like fully define the function, so it follows now that d0 of n is equal to d of n for any n. Yeah. So, and this way we establish the correctness of the definition. So the correctness of definition of d, and we also give the explicit formula for the derivative using the prime expansion, like the expansion of a number into prime divisors, to the product of prime divisors. So yeah, so basically yeah, I think that's it for this video. So there are a lot of interesting properties of this arithmetic derivative, and there are some variations of this notion, and like there are a lot of interesting topics to discuss. But for this video, like, which was just an introduction of the arithmetic derivative, that's it.